So now we'll start with the second part of the tutorial on controllability. So these are the topics which we would cover in this part. So starting from the controllable canonical form, there are two problems on this particular topic because the idea here is to compute the similarity transformation matrix. So here we would discuss two ways of computing the similarity transformation matrix, which would convert the normal or the given AB matrices into the canonical forms. The third way of computing the similarity transformation matrix we would see when we would discuss about the controllable decomposition. There are two problems on the PBH test, two different problems on which is basically the matrix or the rank test. The fifth problem deals with the stabilizable systems, that is, if my system is not controllable, then whether can we say about the stabilizability of the system. The last problem deals with the controllability of the LTV systems. So the problem 1 speaks about that given this AB matrices, which is the linear time invariant system, we need to find the controllable canonical form for this given AB pair. So this problem was taken from this book Encyclis from chapter 3, which is an example 4.11. So if you recall the canonical form of this pair AB, you can directly write that canonical form also by computing the polynomial or the characteristic polynomial. So once you have obtained the characteristic polynomial, then looking at their coefficients, you can directly write the controllable canonical form of this pair A comma B. Now there are other ways. Say for example, if we are able to obtain the similarity transformation matrix and using the concepts we have studied during the theoretical lectures, instead of computing the polynomial, we could directly compute the controllable canonical form. So first we will see one of the procedures to compute the transformation matrix, and then we will compute directly the controllable canonical form. So given this pair AB, you can compute this controllable canonical form, which are written by subscript C, AC and BC. And if we have this P matrix, then by using this equation PAP inverse and PB, we can directly obtain the canonical forms of this pair, which would appear as this. So the last row of this transformed A matrix is basically obtained from the characteristic polynomial. So either for the given A matrix, you first of all write the characteristic polynomial and then obtain the controllable pair, right? So the procedure starts here that we can write the controllability matrix, which is in the standard form BAB up to a to the power n minus 1b of an n-dimensional system. So after computing the controllability matrix, we would compute the inverse of that matrix, and we will extract, or we will take only the nth row of this inversed matrix. The upper elements, we are not concerned with those elements. Once we have extracted the last row of this inverse matrix, then we form a P matrix, which is defined by this Q, QA up to Q into a to the power n minus 1. So this P would result into this AC and BC, which would be in the standard form we had seen in the last slide. Now if we multiply this P matrix which we obtain and the controllability matrix, you would see this P and this controllability matrix, which could be arranged into this form, and finally you can say that it is the controllability matrix of the canonical form. And we have also seen during one of the lectures that the controllability matrices are also related by the similarity transformation matrix, which is given by here. Now you would notice that whatever the P matrix we have obtained, it is also a non-singular matrix because the determinant of P into C we can write as individual determinants of P and the controllability matrix, which is not at all equal to 0, because this is the controllability matrix of the canonical form, so it cannot be equal to 0. If this determinant is not equal to 0, meaning this implies that the determinant of the P matrix itself is not equal to 0. So P definitely qualifies to be a similarity transformation matrix which is non-singular and can be obtained from the controllability matrix. So if we pay attention to the multiplication of the P and B matrix, we will obtain this, which is nothing but the BC, and the multiplication of AC into P would result in PA. So here, if you want to go a bit into the detail of the proof of this equation, you need to use some concept resulting from the Cayley-Hamilton theorem, and the application of that would result that the AC is nothing but PA P inverse. So coming back to the numerical solution of the problem, we have this AB matrix from where we can compute the controllability matrix, and the inverse of that matrix is given by this one. Now since it is a three-dimensional system, we extract the third row, which is this one, and assign it as the Q vector. Now once we have obtained the Q vector and recalling the definition of the P matrix, it would be Q into A and Q into A square. So this would result into this P matrix, and directly applying the equations for computing AC and BC, we will obtain the controllable pair. You can also verify that this last row of this AC are basically the coefficients of the characteristic polynomial of the original AB pair. In problem 2, we are given with again AB pair where X is a three-dimensional and U is scalar. So assume that the characteristic polynomial of A is given by this one, and we define another matrix which is T is equal to the controllability matrix, and another matrix which is composed of the elements or some of the elements of the characteristic polynomial, right? So this matrix is important here. Now the first part of the problem, where we need to show that B is equal to T into this vector. The second part, that A into T is equal to T into this matrix. So this matrix, if you pay close attention, that this matrix is nothing but the controllable form of the A matrix, which has been obtained after some rearrangement of the rows. The C part is that if the system is controllable, then the matrix T, what we have specified in the problem, is non-singular. So one implication of this problem is that this T matrix, which we need to show that it is first of all non-singular if our system is controllable. Now if we see this equation, I can write, let's call this matrix AC. Okay, so I can write AC as T inverse AT, which is nothing but the same equation what we have used to compute the controllable form. So the first way of computing the transformation matrix is we had seen in the problem 1 by computing the Q vector and then determining the transformation matrix. Another method is that you again using the controllability matrix and using some coefficients of the characteristic polynomial, we can define a T matrix which happens to give us the controllable A matrix, and at the same time it would be non-singular if the system is controllable. Also, before even solving this, you would see that from here, if this happens to be our controllable A matrix, so this would be our controllable B matrix, which I can write BC as uh, T inverse B. Okay, so which would be straightforward to verify that T into this vector would definitely be equal to B. So you need to substitute this T matrix which was defined in the problem, this controllability matrix, this matrix which was predefined, and after doing some simplification you would obtain which is equal to B. In fact, this is also one of the implication of the problem we had seen earlier. The part B requires to prove this, if we call this matrix AC again, that AT should be equal to T into AC. So first we take the right hand side of that equation and again writing the T matrix, which then this one is the controllability matrix. This matrix was defined for defining T, and this is the matrix AC. So again, if we multiply these two matrices, we would obtain this by keeping the same controllability matrix. Now we will go on to the left hand side and see if we are able to simplify the left hand side up to this point. So A into T we can write by writing T explicitly into this equation, and this A matrix would multiply with each and every element of the controllability matrix. Now note here that this A cube, I again using this Cayley-Hamilton theorem, I can represent this A cube, or I could substitute A cube by the lower order forms of the A matrix, which you can obtain directly from this part. Let's call this polynomial P of S. Now the Cayley-Hamilton theorem says that P of A would be equal to 0. Now if P of A is equal to 0, so the highest order of the A matrix I can substitute in terms of the lower order of the A matrix. So this is what has been written here. So if we simplify this part, you would, in fact you should try by yourself as well, that you would see that it will come equal to up to this point where we had simplified the right hand side. Okay. About the non-singularity of the T matrix. So one of the concepts we had seen in the part 1 tutorial and also during the lecture slides, that the pre-multiplication and the post-multiplication by a non-singular matrix does not change the rank of the matrix. So since T has been defined as this, so if I want to compute the rank of this T matrix, so this C, if it is full rank or if the system is controllable, and this matrix being the upper triangular matrix would be non-singular as well. So definitely our T matrix would be a non-singular matrix if the system is controllable. If the system is not controllable, then we cannot ensure that T is a non-singular matrix. Okay. And particularly for this problem, since we have defined U as a scalar, so for computing this this C matrix, the C matrix would be a square matrix, right? Because our B would be a vector. Now there is an additional part to the same problem which was also one of the implications of the problem, that if the system is controllable, then the matrix T can be viewed as a similarity transformation that transforms the system into the controllable canonical form. So this T matrix, what we have defined in this problem, also transforms the normal A matrix into the canonical form. So if we aim towards to compute the numerical values, let's take this A matrix as defined by this and the B vector as this. So you can also use some MATLAB functions to compute this polynomial and the controllability matrix, which we have also used here. So if you compute the poly of A, this would result into this polynomial. Now using the elements, this element and this element, we would form the matrix, the post matrix, which needs to be multiplied by the C matrix to finally compute the T matrix, which is a simulated transformation matrix. Okay? So this happens to this one. Right? So there are two ways we had discussed so far. One, so in the first problem, this thing should be noted that we have computed the simulated transformation matrix by taking the inverse of the controllability matrix. Now, if u is not a scalar function, then your C matrix would not be a square matrix. So you cannot use the first method to compute the simulated transformation matrix. But you can possibly use this method to compute the transformation matrix, because here we know inverse of the controllability matrix is involved. Okay. The problem 3 is on the PBH test for controllability, where we need to show that the state equation, which has been already partitioned into the block matrices, is controllable if and only if the pair A22 and A21 is controllable, assuming that B1 is a full rank block matrix. So this problem was taken from another book, Chain. It is an unsolved problem number 6.4. So one point we need to recall here, that whenever we had discussed about the controllability, we have always discussed if we want to visualize that controllability, our A matrix is the state matrix and B matrix is the control distribution matrix. But if we want to compute just the rank of the controllability matrix, they are just an pair, AB pair. Now, both these block matrices A22, A21 are not, or any of the element of this pair does not belong to the control distribution matrix. So here we are concerned only with the controllability of this pair, meaning to say that the same formula we can use by using A as A22 and B as A21. Okay. So we need to show that whatever the controllability matrix we would form using these two pairs or using this pair, it should be a full rank. So recall from the lecture slide number 15, where we have given the PBH test, the necessary and sufficient condition for the controllability of the pair A, B, that the rank of this matrix, which is found by A minus lambda I and B, where lambdas are the eigenvalues of this A matrix, has full row rank at every eigenvalue. Okay. Now if we substitute our partitioned A matrix and the partitioned B matrix, which is given in the problem, let's call that matrix M. So that matrix we would obtain as this one. Now here one important thing to notice, that B1 is already assumed to be a full rank matrix. Now if B1 is a full rank, the rank of this matrix would be a full rank, which definitely would be less than n. Right? Now for this pair, let's write this pair explicitly. So it would be A21 and A22 minus lambda I. Okay, the second row of this block matrix, I can write this matrix as A22 minus lambda I and A21. Right? The rank of this matrix would definitely be equal to the rank of this matrix. Now if you see the similarity between the rank condition this one and the rank condition this one, it says that if this A22 and A21 pair is controllable in this sense, in the sense of PBH test, then we could say the rank of this overall matrix would definitely be equal to n, right? So this is becomes the necessary and sufficient condition for the controllability of the given AB matrices, if and only if this A22 comma A21 is controllable. Okay. Now in this problem, we are given the numerical values of the AB matrices, and we need to compute the uncontrollable eigenvalues of the system using the PBH test. So we have studied that if the system is controllable, the rank of the controllability matrix would be a full rank. In this case, it would be equal to 3. Yeah? Now, if the rank is not equal to 3, we can find that for what eigenvalues the rank is or the matrix is or the pair is controllable deficient, let's say. So we want to compute those eigenvalues for which the system is uncontrollable, in the sense that if we follow the PBH test, and since the PBH test includes the eigenvalues, so we could compute explicitly that for what eigenvalues our system is controllable and what are the uncontrollable eigenvalues. So proceeding in the similar way, so first of all we would compute all the eigenvalues of the matrix A, which are given at 0, -1 and -2, and for all the eigenvalues we will start computing the rank of this matrix, and for the eigenvalues for which the rank of this matrix becomes less than 3, it automatically becomes the uncontrollable eigenvalues. Okay. Now another implication of this, you can see that since lambda is equal to -2 is an uncontrollable eigenvalue, now if we recall our stabilizability concept, that this eigenvalue is a stable eigenvalue, though the system is not controllable, or let's say not completely controllable, but it is still at least stabilizable. Okay, because the stabilizability test speaks only for all the eigenvalues which are on the right hand side. Okay, now here neither or for the eigenvalues for which it becomes uncontrollable, it's on the left hand side. Okay. So without even testing for the doing further test, we can say that this system is at least stabilizable. Problem 5, here we need to check the controllability of the system, and we need to comment on the stabilizability using controllable decomposition procedure. So far we have been doing different ways of compute or determining whether the system is controllable or not. So here, so we forgot to write this U. So using this AB pair, either you can compute the controllability matrix, or you can compute the eigenvalues, and then you could see for what eigenvalues the system becomes uncontrollable. So we'll go directly with the controllability matrix, and you would see that the rank is 2 and it is not equal to 3. So the system is not completely controllable. So in this problem, you would see another way of computing the similarity transformation matrix, which would convert not into a canonical form, but it will give us a decomposition. There are different ways of doing the decomposition. In fact, when you were doing the or computing the canonical forms, it is also one sort of decomposition. So here, since the rank is 2, it means that there are at least or there are at most 2 independent linearly independent vectors. So looking at the controllability matrix, we can pick these 2 vectors, the first vector and the second vector, as the linearly independent vectors, and we can select another vector which is again, so that all these three vectors become linearly independent. So the third vector is 0 0 1, and then writing all these three vectors would give us a T matrix which is non-singular because all the vectors are linearly independent. Okay, now using this T matrix and using the same formulas for the transformation, we can compute these two matrices A tilde and B tilde, where you would notice that this A tilde and B tilde are not exactly in the canonical forms. Okay, so here, from here we can extract the controllable and the uncontrollable part. So this top row, which is 0 minus 1 1 2, and another the block, or let's say the vector 1 1. So this pair a1 b1 is a controllable pair, and the uncontrollable pair is this one. Okay, so we can express the overall system into this decomposed form, where a1 b1 becomes a controllable part of the system, and since the eigenvalue of the uncontrollable system is at -1, so the system is at least stabilizable. Okay, for again whatever the concepts we had studied in solving the problem number 4, you can use those concepts. That is to say, first of all compute all the eigenvalues, and then see for what eigenvalues the system becomes uncontrollable. Now if that eigenvalues is on the left hand side, then the system is stabilizable, and if that eigenvalue is on the right hand side, then the system is not stabilizable. So this problem is also on the controllable decomposition, the numerical computation of the controllable part using the decomposition method, where B matrix is now 2 cross 3 cross 2 matrix, so meaning to say we have two control inputs and one output. So checking the rank of the controllability matrix, we see that again it is rank deficient, so meaning to say the system is not fully controllable. So here we use the same method again, that we can find at most two linearly independent vectors which we can extract from this C matrix and they are happen to be the first two columns of the transformation matrix, and again the third vector has been chosen such that the Q matrix becomes a non-singular matrix. So again computing the canonical forms or by the transformations by using this P or Q matrix, we could obtain this A bar matrix, B bar matrix, and from here this part would becomes a state matrix of the controllable part of the A system. Okay, and the rest of the part would become goes for the uncontrollable system. Okay. Now this is the last problem where we discuss about the controllability of the LTV system. Here we have taken A as a constant matrix, but B is a time varying matrix, and this problem is taken from another book which is not mentioned in the references, but this is, you can also take a look at it, the book by William Terrell by Stability and Stabilization, and we have taken this example 4.11. So we need to comment on the controllability of this LTV system. So this problem is quite interesting in the sense that for the LTV system we can compute, if we want to concretely answer the controllability of an LTV system, we need to compute the Gramian, the controllability Gramian matrix. So this was one way. Now we had, if you recall, that for computing the Gramian matrix, we need to compute the state transition matrix, and a state transition matrix for an LTV system is pretty much complex. Now, fortunately, here the A matrix is a constant matrix. So the state transition matrix would definitely be an exponential matrix. So you can compute it here. But if the A matrix is also a time dependent matrix of not that specific form which we had discussed during the lecture slides, then it would be difficult to compute the state transition matrix. So to circumvent that issue, we compute another matrix which was the M matrix. If you go to the lecture slide number 39, so there we had given uh, basically the sufficient conditions only for the test of controllability, because once you have computed the controllability Gramian, then it is a necessary and sufficient condition if the rank of this controllability Gramian is a full rank for all time T0 and T. Now the way we have computed this M matrix is detailed into the lecture slides. Now if the rank of this matrix M0 and M1 is happens to be 2, then it would definitely be controllable. Now the rank of this matrix is less than 2, which is 1, and being the only the sufficient condition, we cannot guarantee that whether our system is completely controllable or not. Okay, so you can also compute by yourself the controllability Gramian, and you would notice that the rank of that controllability Gramian would also fail, or would also be less than 2, meaning to say that the system is not completely controllable. But what we are interested in, that whether if we could comment more into detail about the controllability under some condition. So for that we would investigate the solution of this system. So the general solution for this system where the A matrix is a constant matrix and the time varying terms are only in the B terms. So we using the variation of constants formula, we can write the solution for x1 and the solution for x2. Okay. Now if you recall the definition of the controllability, the controllability says that from some, let's say this time is t0 and this time is t, that from some non-zero value we need to reach to the origin in time t, meaning to say, or let's say we call this at time t1. So if I need to reach at t is equal to t1 is equal to 0 from some non-zero initial condition that are x10 and x20. Okay, so if I write these two equations explicitly, I would have x10 plus 0 to t1, because now I have replaced t is equal to t1 both sides. Over 2 is equal to 0. Equal to 0. Now if you pay attention to these exponentials, these exponential would always be non-zero. So these two equations can become 0 only if these are equal to 0, right? Meaning to say that x10 would become in that case equal to d tau, and my x20 becomes equal to the same as x10, right? Meaning to say that if we see in the x plane, let's call that x1, let's call this x2. So if my initial conditions are along this line, if my initial conditions are along this line, then in that case I would reach towards the origin. which speaks about which is completely in coherence with the definition of the controllability. Starting from any point which lies on this line, this should be 0. Starting from any initial condition lying in this point, the system is controllable. Now, if you choose any other point which does not fall onto this line, you can never reach to the origin in finite amount of time. Okay. So we under this condition that both the initial conditions must be same, we can say our system is controllable. But if both the initial conditions are not same, then the system is not controllable. Now, just for the validation, you can see that whether the rank test of the controllability matrix is also applicable to LTV system, as it was a necessary and sufficient condition for the LTI system. So if we compute this controllability matrix by taking this time varying terms A and B, we would obtain this controllability matrix. And this matrix is a non-singular matrix which says that it is controllable. And this is also one of the conclusion that the test what we had seen for the LTI is not applicable for the LTV systems. Okay.